आधा ऐसे हो पूरा चंद्रमा ओ तारा तेरा
So I think we can start. So I think we can start now. So are the slides visible? Okay. So I think in this week's like lectures, you had covered about various features related to microscopy, which involves depth of field, resolution, magnification, how various corrections are done to optical microscopy. So we will try to do some questions on that today. Because this was a class which is much more of a theoretical, so we'll have less number of questions today. So first, starting with the first question that says, what is the resolution of a human eye? So I want you to answer these questions so that I will also mark them here. So what is generally the resolution of a human eye? Is it 1 mm, 0.1 mm, 2 mm, or 0.2 mm? You can try to answer the questions. Anybody?
Point two.
Right, we have the minimum resolution of a human eye is around 0.2 mm. That means we can resolve between 2 points which are at a distance of 0.2 mm. So we can resolve these two components or two objects if the distances between them are 0.2 mm. Okay. Then we have another question that says that marginal rays focuses near to the lens, away from the lens, and does not focus. So what could be the answer for this? So basically we have this comes under the spherical aberration part where you have a optical line or optical axis and you have a lens, and when the rays pass through it, they can pass through this part of a curvature or they can pass nearer to the center. So there will be one ray that will be at the edge of the lens and one will be closer to the center of the lens. So this rays are called as marginal rays, while the rays which are closer to the center or closer to the optical axis, they are called as paraxial rays. So these are two types of rays, and when they pass through a lens, they are they tend to be focused at two different positions. That is why it leads to spherical aberrations. It leads to aberrations in the images that you are obtaining. So the marginal rays which are falling on the edge of the lens, they are converged at a point which is very closer to the focus, right? Which is closer position to the lens, which is at a closer position, while these rays which are paraxial rays, they tend to be focused at a far point somewhere here. So for a marginal rays, the right answer is that the light focuses nearer to the lens, while for a paraxial the rays focus far away from the lens. So that is why we have two different points where the image is being formed, and that is why it leads to aberrations in a image, because there is not a single discrete point where the image is being formed. So the right answer is nearer to lens. Next question is, achromatic objectives are corrected for uh, to bring the red and green to common focus, chromatically corrected to bring red, blue, and green to common focus, chromatically corrected to bring red, blue, deep blue, and green to common focus, and chromatically corrected to bring red and blue focus. So these are related to your chromatic aberrations, right? Chromatic aberrations is nothing, that is because we have a light which is composed of different wavelengths. So each wavelength will pass through the lens in a different way. For example, if we have a white light, it is composed of various bands of wavelengths, right? So we usually represented by Webb-Quire. So we have different wavelengths for these. So we can say that if you have a smaller wavelength, it will be focused at a different point, while if you have a larger wavelength, it will be focused at a far larger distance from the lens. So we will have two different places where the wavelengths will be concentrated or focused. So that will result in chromatic aberrations in the lenses. So to correct such chromatic aberrations, which are because of the difference in the wavelength of your light or source, so we are using the objectives which are chromatically corrected, which are achromatic objectives, that they do not have a they will not segregate into different wavelengths. That is why they are achromatic objectives. So normally the corrections for such objectives are done for what? It is majorly done for red and blue. So I think the right answer is D. So these chromatic objectives, the corrections are done for red light and blue light, while we have seen that for objectives which are we are trying to use a single green, like green filters in the microscopes, that will you tend to use only the green light, and because of that there will be requirement of no chromatic aberrations because we have a single wavelength. So normally achromatic objectives are corrected to only red and blue wavelengths, and they are corrected to bring them to a common point, so we do not have the aberrations in the image. So we have only one common point where both wavelengths come to a focus. So these are the corrections that are done due to chromatic aberrations in the lenses. Next, we have a question that is based on ASTM grain size number. So the question says, determine the ASTM sorry, ASTM grain size number if 256 grains per square inch are measured at a magnification of 100x. So you know that for a ASTM grain size, we mostly have to define the magnification. You will always see the magnification, because if you have a image which is at 100x, you will tend to see grains which are somewhat like this. Say for example, if we see something like these, but if you go for a higher magnification, say for example now you go at 1000x, you may be able to see, say for example, only this much grain, only 2 grains maybe. So this is because you have to define the magnification. At your smaller magnification, the number of grains will be larger, but if you go for a larger magnification, the number of grains will decrease, because you are focusing on a very small area and you are at a higher magnification. So now you have to determine the ASTM grain size number if 256 grains per square inch, this is the area which we are monitoring, or the area which we are analyzing through a microscope. So we are given the area of area and the number of grains in that area and the magnification. So you know the formula for ASTM grain size number. It is given by something like this, right? So you have to estimate the ASTM grain size. Normally we write this as, I think better to write that way. So we mostly write it like this. You have to find this ASTM grain size number. This small n is the number of grains per square inch at 100 magnification, because the magnification is given. So you do not have to worry about the magnification, and you have to calculate this capital N, which is a grain size number. I want you to take a minute and try to solve it. Then we will solve it. If you can attempt to solve this question. You just have to put the values in the equation. So you have to put this n as 256, and you are given 2 raised to power the n minus 1, which you have to find the ASTM grain size number. So how will we solve it? We can use a log scale. So we can apply log on both sides, and then we can solve it. So we can say log of 256 is equal to log of 2 raised to power n minus 1. So what is log 256? So you have to just solve it and determine the n. You can also write this part of a right hand side of equation as n minus 1 multiplied by log of 2, right? Because this is log m raised to power n. So you can write it as n log m. So this is your final equation. So you can tell me what is the answer for n. You have to just solve log of 256 and log of 2. Can anybody solve it? What is the value of n?
Man, I got 9.
Okay, so the 9, how did you get 9? Because okay, you have log of 256 and plus 1, right? So the answer is 9. So that is the right answer. So the ASTM grain size number will be 9 when you have 256 grains per square inch of the sample of the microstructure available at 100 x. Okay, so we can go to next question.
Excuse me, ma'am.
Yes.
Ma'am, in this formula, which says n is equal to 2 raised to n minus 1, can we apply this formula for magnification other than 100x?
Yes, we can. We will do that. One question on that also. We can. We have to change, because this is particularly for a magnification 100x. So you have to incorporate the magnification part also in the equation to do it
Okay, ma'am.
at some other. So we will do some one question on that also.
Okay.
Okay. So now we have another question that says resolution of a microscope is A, smallest distance between the 2 points for them to be seen as separate points. B, it is same as magnification. And C, it is dependent on wavelength of the electromagnetic radiations used. So which is the right option? You know what is resolution? So resolution is always, as we said, that it is how we are
A, I
able
think.
to resolve the two components. So the what is the smallest distance that we can see these objects as distinct objects. So A is the right option. It is saying that resolution of a microscope is same as magnification. This is not true, because resolution is only how clearly you see the two objects. It has nothing to do with like it has a at what magnification you are seeing, the resolution will be affected, but it is not same as magnification. So it has nothing to do with magnification. And the C point says that it is dependent on wavelength of the electromagnetic radiation. This is also right, because when you write the formula for your resolution, it is something like dependent on your wavelength. So according to Rayleigh's criteria, it is something 0.61 lambda, which is the wavelength of the electromagnetic radiation, divided by the refractive index of the medium from which it is of the lens, and we are having sine of alpha. Alpha is the uh, angle of your aperture, like how you are making the rays fall on the lens. That will be determined by alpha, how much rays are allowed onto the sample or onto the lens. So we are saying it is dependent on wavelength, it is dependent on refractive index and alpha. So it is dependent on wavelength of the electromagnetic radiation is also right, and the smallest distance between the 2 points is known as the resolution. So that is also right. So both these options are right. Okay. Now, just based on the same concept of resolution, we have a question that says calculate the resolution of a microscope in micrometer with value of lambda given, the value of your refractive index and numerical aperture given. So you have to calculate the resolution of a microscope using the same formula. So you know what is the formula for your resolution. You know the numerical aperture. The numerical aperture is nothing but it is the this part, the mu sine of alpha. This is your numerical aperture part. Okay. And we have the 0.61 lambda times the numerical aperture. So you just have to put it in the formula. The resolution will be equal to the 0.61 multiplied by the wavelength, which is 500 nanometers here, and divided by your numerical aperture, because you are given the refractive index, you are given the numerical aperture. So you can say it is 1.4. Now you solve this and tell me what will be the resolution.
Two 17.85.
217.85. Okay. So which is with the part B or part C? Because you have to give it in the micrometers. Remember, you have to give the answer in micrometers. So the answer will be first you will be, because this is 500 nanometers, so I think it will be 217 nanometers, and then you have to convert it to your micrometers, so it will be 0.217 micrometers. So I think this is the right option, the option C. Is it okay?
Yeah.
Okay. So then we have another question. Okay, 1 second. So I think now so we have question that says what is the minimum separable distance between features that can be resolved by a microscope using the light of 400 nanometer wavelength. So this is just nothing. This minimum separable distance is only talking about the resolution. So we have to find the resolution, and you are given that you are using a light of 400 nanometer wavelength. So you are having given a wavelength of your light source, and it has a refractive index of a lens have 1.4 and aperture angle of 150 degrees Celsius. So sorry 150 degrees. So you have to find the resolution for this. Again we'll be using the same formula. Resolution is equal to 0.61 times lambda divided by mu sine of alpha. So you are given the wavelength, you have been given the refractive index and the aperture angle. Remember this is the complete aperture angle, while this alpha is only the half of this angle. So like if you know you have a lens like this, and you have some aperture here. So this complete angle that is being formed, this is the whole angle is a aperture angle, but because we are only concerned with half of that angle, we are only concerned with this angle, so that will be given by alpha by 2. Here it will be given by alpha by 2. So remember that your this angle is actually a semi aperture angle, it is not a complete aperture angle. Semi aperture angle, while the angle here given is a complete aperture, so you have to divide by 2. So based on that you can find the resolution. So you can put the values in this formula and calculate the answer, which is 0.61 times the lambda, which is 400. This mu is the refractive index, that is 1.4. Sine of angle, which is 150 divided by 2. So now you can calculate the answer. This is 1 point. You can tell the answer if you have calculated. What is the right answer?
Point 0.18 micrometers.
Okay, so the right answer is 0.18 micrometers. Right. Basically, you can see that this is the resolution that the microscope is providing, but you have seen that for a human eye, you have a 0.2 mm, say for example, resolution. So the this is the amount of times the microscope is trying to resolve the image for you. So this is 0.18 divided by 0.22 will give you the number of times the resolution of your image, resolution of your object is being increased, like for your human eye to see. So we can do to the next question. It says now this is a question that is on a different magnification. So it is saying that what is the number of grains measured at 300 magnification. Earlier we saw that the equation was valid for 100x magnification. So now we have 300 magnification. In 1 square area is 14. So you are given the value of your normal number of grains, which is n, that is 14 here, and you are also given a magnification of 300. So you have to find a ASTM grain size number. So whenever you have such equations, you have to consider the magnification at which the image is being taken. So as I said, that if you are going for a higher magnification, the number of your grains that are visible will decrease because you are at a higher magnification, while if you are at a smaller magnification, the number of grains will be more. So to cater to this magnification part, the ASTM grain size number equation is modified like this, that is n is equal n, which is your number of grains, and then we multiply it with the magnification at which the image is being taken, divided by 100 and square, is equal to your normal, what it is, to n minus 1. So you have to find this ASTM grain size number. You know rest of the values, so you can find the value of the ASTM grain size number. So you have 14, and then you have 300 by 100, so we can write 3 square is equal to 2 raised to power n minus 1, right? So you will have something like 126 is equal to 2 to the raised to power to the n minus 1. So now you can calculate n by applying log on both sides. So it will be log of 126 is equal to n minus 1 log of 2. So now you can calculate n.
Eight.
Right. So the right answer is 8. So you have 8 is your ASTM grain size number. But you see that earlier also you had a somewhat ASTM grain size number around 9, but the number of grains that were present were 256. So the number of grains were larger at 100 because it was at 100x. That is why you had a large number of grains present for a similar ASTM size grain size. But now the ASTM grain size is 8. It is, but the number of grains are only 14 because you are at a higher magnification, right? So it depends on your magnification, how much you will be able to see in a particular image. So it is always important to uh, note down your magnification, note down your scale, especially also if you are using your calculation of your methods where you are using line intercept method or any other method for a measurement of your grain size or phase fractions. Then also you have to ensure that you note down the scale, the magnification scale that is present at the micrograph, because that will ensure the number of grains that you are seeing in your micrograph in a per unit area or per unit square inch of your area. So the magnification part needs to be mentioned every time when you are dealing with micrographs or related to grain size measurements. So next we have another question that says calculate the depth of
Excuse me, ma'am.
yes.
Ma'am, in this question in which we are going through some quantitative microscopy, how did we came to know that these number of grains are present? Do we go manual counting?
Number of grains are measured. Yeah, it is done by line intercept method. You can do with that. There are also
Yeah,
softwares that
yeah.
do the number of grain measurement also nowadays. So I think based on how it is interacting with your lines that you are being drawing, the software calculates the points of intersections and gives you the results, or you can do manually also. So I think both ways is possible.
Thank you, ma'am.
Okay. So next is the question: calculate the depth of field of a microscope using light of 400 nanometers wavelength and refractive index 1.7 and semi aperture angle 60. Here you are given the semi aperture angle. So you have to calculate the depth of your field using the formula. So 1 second. Okay. So we have first, what is the depth of field? Depth of field is defined for your objective, right? That how much distance you can move without changing your the quality or the clearness of your image or the sharpness of your image. That is known as the depth of field for a microscopy. So you have to calculate based on your formula for depth of field here, which is given. We know that it is given by 1.22 times the lambda divided by mu times sine of alpha, which is your semi aperture angle, which is given here, and you have tan of alpha. So you can put the values of your wavelength, which is 400. You can put the value of your refractive index and the semi aperture angle to calculate the depth of field. Okay, so we can write 1.22 multiplied by the wavelength, which is 400, divided by the refractive index, which is 1.7, and we have sine of alpha, which is sine of 60, and we have tan of 60. Okay, so now you can calculate your depth of field. So you can tell me the answer once you have calculated it. So have you calculated?
Ma'am, I have got answer as B.
191.4. Okay. So the right answer is B. So that is your depth of field. So you have to see that the dependency of your depth of field depends on your refractive angle, depends on this semi-aperture angle, and it also depends on the wavelength that you will be using. So next question will be about when increasing the
Excuse me, ma'am.
yes,
Ma'am,
yes.
I have a questions regarding depth of field and depth of focus.
Okay.
Like in this question, we have got very small value
Yes,
depth of field.
yes,
Now,
yes,
if we try to estimate the value of depth of focus
yes,
for the same setting, ma'am. Okay.
yes.
So, ma'am, don't you think it is a very insignificant of for human eye? See, we are getting a 191 nanometer as a depth of field.
Mm-hmm.
Okay. And suppose we are using a magnification of 100.
Mm-hmm.
So 100 into 100 into 191 nanometer.
Mm-hmm.
That will be, I think, depth of focus for the eyepiece.
Right, right.
So, ma'am, this value is very, very tiny.
Yes,
Okay, the depth of field is also very small, and obviously the depth of focus will also come out to be very small. So,
yes.
ma'am, how significant these values are when we are concerned about the eyepiece only? Because these small values, if you try to adjust, particularly say human eye,
Mm-hmm.
so how human eye can adjust these small values?
Like for these values, these are just for your for a microscopy level. Whenever you are having a objective lens, and then you have a plane where the objective lens is focusing, so at that point of focus you have to see that it is just how much distance you can change without actually changing the quality of your image or the sharpness of the image, right? So 191.4, it looks like a very small value for you, but when you are in a microscopy setup, it is enough for a clear image to be seen, because this is not something that we are trying to resolve or we are trying to adjust. This is something related to the microscopy. For this is though this is for a normal microscopy where you have an optical microscope and you have a refractive index, these values will be much higher when you go for say higher resolution microscopes, because you will be using a different wavelength, and the refractive index will also be affected. So and also the aperture angles are also very much adjustable in those microscopes. So this looks like a small number because it is a small number, but when you are in a microscopic configuration, it is enough for a object to be seen without changing its sharpness, because you will be going for a fine focusing or coarse focusing, so that will help you to adjust this value. So it is not what we see to the human eye, but it is more of a microscopic setup.
Actually, ma'am, my doubt was that from this value which we have got just now, 191.4 nanometer, we can calculate the value of depth of focus also using the formula which
Yes,
sir has told during their lectures.
yes,
Okay.
yes, yes,
Now, my question is that if I try to calculate the value of depth of focus,
yes,
okay, that value will be related to your eyepiece or human eye. That was my question.
yes, yes,
That means the variation we will get by finding the value of depth of focus. Okay,
yes.
that variation should be applied to the eyepiece lens or human eye. That was my question.
That will be applied to the because it is only for the I think it is for a fixed position of an object. So I think it will be applied for a eyepiece only, because that will be how you can change the image formation. How much change you can get in your image formation based on the change in your depth of field. So, but for a fixed object, so the object is fixed.
Okay.
You can change your eyepiece distance or image formation distance. That
Yeah.
will be, I think it will be related to the eyepiece only, because you will be changing the distance only.
That means, in short, we can say the depth of field is applied to objective lenses and the depth of
Is
focus is
applied to
being
the
for
eyepiece, yes.
eyepiece.
Yes,
Okay, ma'am. Thank
yes,
you.
yes. Okay, so we have another question that says, one second. Okay, so we have something, next question, which says, when increasing the magnification on the microscope, which of the following occurs? The depth of field increases, the resolution limit decreases, the visible area decreases, the contrast increases. So you have to tell which of the following option is right. So see, for a magnification and the depth of field, are they related or not? You just have to see the magnification. If you are changing the magnification, you are just increasing the area that is visible in a micrograph, right? You are just increasing the number of say you are decreasing the number of grains in your structure. You are going to a smaller and smaller area to see at a higher magnification. But will it affect your depth of field? Is your depth of field affected by magnification?
Madam, I think no.
So no, the depth of field is not a function of your like magnification. And then the second says it is a resolution limit which is decreases. So the resolution limit is also nothing but it is related to your same the arrangement of your microscope. So it is refractive index, the your semi aperture angle, and your lambda. So resolution limit will also not be affected because the minimum distance what remains between the two objects will remain the same if you are having a particular microscope with a particular parameters, right? So that will not be affected. And the C option is that the visible area decreases, which is true because now you are at a higher magnification and the area that you are seeing will decrease. So the visible area decreases is the right option for this. Whenever you are going for a this increase in the magnification, okay. So next question is, how should the initial focusing of the microscope be done? With the coarse focus moving the lens towards the specimen, because when you will be coarse focusing, you will be changing actually the working distance between your sample and your objective lenses, right? Your when you are focusing any object or any surface, you are actually changing the distance between their lens, objective lens, and the sample, sample height, right? So it says, should the initial focusing be done with coarse focusing, or so that you move the lens towards the specimen, or it should be done with fine focusing and you move the lens towards the specimen? So there are fine focusing, coarse focusing, but both are moving the lenses towards the specimen. The third option is that you are doing the coarse focusing and you are moving the lens away from the specimen. And the fourth option is that you are doing fine, but you are moving lens away from the specimen. So which of this option is right? Because whenever you are changing actually the objective lens, you are whenever you are seeing any objective whenever you are going for an optical microscopy and you are changing your optical lenses, so you start with your smallest lens, then you go to your higher lenses. So as you change your lenses, the lens working lens, the distance between your object and between the sample and your objective lens is automatically changing because they're of different dimensions. You'll always see their objective lenses are of different dimensions. So you have to continuously focus your sample with the respect to your objective lens. So you have to say how you should do the initial focusing out of the four options.
Okay. The with force focus moving the lens towards this.
So what we should do? Actually, whenever you're doing a focusing, you should always try to do the first the fine focusing, and then it should be away from the specimen, because whenever you're changing the lens, if it goes from a, say for example, 10x to 50x, the distance between your objective and the sample is automatically decreased when you're changing, going to a higher magnifying lens, higher objective lens. So you might end up crashing your sample onto your objective lens. So always you should try to move away the sample from the objective and then do the fine focusing, right? Fine focusing this way that you move away the sample from the lens. That is the ideal way, because otherwise you will be crashing the sample into your specimen, like the specimen sample will be crashing into your lens. So to avoid that, you should be doing first fine focusing and then it should be away from the specimen. Okay. Then we have the question that says, when the aperture stop is made smaller, which of the following occurs? The depth of field increases, the resolution decreases. The aperture stop is nothing but your angle of alpha, which is a semi aperture angle. So you have this angle. It is saying when you are trying to make it small. So you know the relationship between your resolution and your angle, which is 1 by sine of alpha. And you also know the relationship between your depth of field and aperture angle. So that is something related to your sine of alpha and tan of alpha. So if you're trying to decrease this alpha, so what will happen to your resolution and depth of focus? So if you are decreasing your alpha, say for example, first for resolution, if you are decreasing your alpha, you are trying to increase your resolution, right? The resolution, you are trying to decrease your resolution actually, because the value of sine of alpha will decrease, this value will increase. So the minimum distance that you will be resolving will increase. So you are decreasing your resolution. So the resolution will decrease. This is the right option, because based on your angle of semi-angle aperture, the resolution will decrease. The question comes now for the depth of field. So if you are decreasing your alpha, what happens to your depth of field? It increases, right? So the depth of field will increase. So both options are right. So you can say that when the aperture is made smaller, you will always have a decrease in your resolution, and you will have a increase in your depth of focus. So these two are actually inversely related. So you have to find an optimum balance between your resolution and your depth of field to have a optimal configuration for your microscopy, right? So this is something that will, because this is something that you can control. For example, for all optical microscopy, the wavelength will be fixed, your refractive index for the lenses will be automatically fixed. So this is something that you can tune and you can change. So the aperture opening can be controlled, and that will help you to control your resolution and your depth of field, right? So I think that is it. If you have any question, these are
Ma'am,
this was
yeah,
the last
ma'am,
question.
in the last question, you said the resolution decreases as we make the aperture angle smaller.
Yes.
So, ma'am, my question is that do you mean resolution decreasing means the value is increasing, the value of R is increasing? Am I right?
Yeah, right.
Yeah.
So if the R is increasing, so that means you will have a minimum distance that you will be able to resolve the two objects will be more. It will be, say for example, 2 mm. But if
Yeah.
you increase the aperture, now when you have a better resolution, instead of 2 mm, you will be having 0.2 mm. So that is better. If you have a 0.2 mm
Yeah.
resolution, that means you can go to a smaller distance between the two objects and you can clearly see them. So that means they are better resolved if their value of R is smaller.
Okay, ma'am.
Okay. So I think that is all for today. So if you have any questions.
Ma'am, I have a question from the week 1 assignment.
Yes.
In this assignment, there is a question number 6. I think the theory part has been not covered by the sir.
So what was
Question
the
is related to
yes.
The question is related to Burger vectors.
Okay.
I think the theory part has not been covered.
Maybe it will be covered later. What is the question?
Ma'am, it is asking, let me tell you the question. Madam, the value of A is given to us, the
Yes.
lattice constant, 6 angstrom.
Okay.
And what is asked is, what is the magnitude of Burger vector of a dislocation in an FCC crystal
Yes.
with A equal to 6 angstrom?
Okay. So you are given your Berger. You're supposed to find a Berger vector for a FCC crystal. So there is a specific formula for a Berger vector for each crystal, for FCC, for BCC type of crystals based on their value of this lattice parameter. So we can maybe cover such questions in the next class. I will check it and then I will cover these questions in the next class.
Madam,
Okay.
the problem is that the last date of submitting the assignment is 7th.
Is
7th of February.
okay. So actually, you just don't have to do anything. Basically, whenever you are trying to see Berger vector, the Berger vectors are always related to their lattice parameters, right? So this
Yes.
how they are related. There is a particular formula for each crystal, whether it is FCC, whether it is BCC. So you just have to put in your value of A and B. So normally when you are seeing a Berger vector, it is related to your dislocation moments, like how your lattice will be distorted and how much it will be moving in which direction. So these are actually the close pack directions of your crystal structure. Okay, so you just have to put in the formula for your value, like for your plane. For example, for FCC, if you have a close packing along 110 plane, so you just have to put in the value of 110 and then multiply it by your lattice parameter and divided by 2. So there is a specific formula for Berger vectors related to their this close pack directions. So you can check it for now and then we can cover it in the next class.
Ma'am, I have tried to solve by searching the formula on the internet, but the issue is that the HKL value is not given in this question.
Yes, you have to see because it is an FCC structure, then you might have to see your close back direction. So you have to always know what is the close back direction for your FCC, for a BCC crystal, for a FCC crystal. So that will be given. It is
And that is not
you have to know
that is
the
not given in the question.
yeah, this will be always known to whenever you are going for a crystal geometry, you should always know the close pack direction for both close pack plane and a close pack direction for a FCC
Yeah.
crystal and a BCC crystal. So if there is, for example, along FCC, if it is along 110 plane, so that is the plane and then you just have to put it in the formula.
Okay, ma'am, got it.
Okay.
Madam, I had a question.
Yes.
Can you hear me? Madam, will you be able to explain me how to draw bar 1, plane for a cubic crystal?
Again, what is the plane?
Bar 1, 1.
So this is a plane given in so you just want to draw this plane.
Yeah.
So okay, so if you have a, say for example, you have a crystal structure, sorry, you have a unit cell.
Yeah.
And you want to draw bar 1. I think this is what you want to draw, bar 1, 1.
And 1, yeah.
Okay, so you are having 3 directions. This is
yeah.
A,
Right.
this is B, this is your C. So
Yeah.
first, if you have to go 1 bar, that means you have to go along the negative axis. So from here, you
Yes.
will
Yeah.
choose your because you have to know negative y also. So this you have to choose this as your origin. This is your
Okay.
origin. So -1, and then this will be -1, and then it will be 1 in the positive direction. So it will be something like this. I hope it is clear. Something like this. Because
so this is the origin.
This is the origin. You have to choose the origin where you can have a negative A and a negative B. So negative A will be inside like this. This is your negative A. And for negative B, you have to go along this direction. opposite to the positive. So this is your point for B, this is your coordinate for A, and then along C it is in positive direction. So this is your positive direction.
Yes.
So this is the point. So you just join them and then you'll find the plane.
Yeah.
Is it clear?
Yeah.
Okay.
Thank you.
Okay. Okay. So that is all for today. Okay. Thank you.